Welcome to the lecture series on process integration. This is module 5, lecture 3. The topic of today's lecture is application of PDM for MER Hen synthesis, meaning that we will apply the pinch design method or pinch design rules which we have in the last lectures to design a maximum energy recovery heat exchanger. To apply the PDM for the MER Hen design, we have selected a stream table given here. There are 2 hot streams and 2 cold streams for which the heat capacity, flow rate, source temperature and the target temperatures are given. The Hen has to be designed for delta T minimum equal to 10 degree centigrades. Now, this is the stream diagram or the grid diagram for the problem. The pinch temperature is hot pinch temperature is 90 degree centigrade and the cold pinch temperature is 80 degree centigrade, and QH minimum is 87 kilowatt and QC minimum is 40 kilowatt. This has been observed, this result has been observed from PTA. That means, we have already done the utility targeting, and from the utility targeting this result has come, that is QH minimum is 87 kilowatt and QC minimum is 40 kilowatt. Now, if I am going for a MER design, maximum energy recovery design, then my developed Hen will show a heater having 87 kilowatt and a cooler having 40 kilowatt, and the design will confirm this targeting results. Here we will see that a number of alternative designs can be developed using pinch design rules or pinch design method. In this problem, I have developed 2 hot end designs, in fact 3 hot end designs and 3 cold end designs. As hot end and cold end are thermally disconnected, the hot end is separately thermally balanced and the cold end is separately thermally balanced. So, the designs which we have developed for hot end and the designs which we have developed for cold end can make different combinations, and we can have many designs of the Hen. This we will see. Now, to start with, in the upper part we see the design 1 is shown here, and the lower part the design 2 is shown here, and both are for the hot end of the problem given in the stream table. This is the CP table which we have already talked during the pinch design rules. Now, if you see the CP table, it writes here above pinch hot end design. That means, this CP table is for hot end and above pinch area design. The rules which we have to follow are 2 rules. NH should be less or equal to NC, that means, number of hot streams should be less or equal to number of cold stream. This is the first rule. The second rule is CPH, that is Cp of the hot stream should be less than or equal to Cp of the cold stream when we are putting up a match. and here it shows that only one hot stream is present and its Cp is 3, and 2 cold streams are present whose Cp is 3.5 and 4. So, there are 2 cold streams here, Cp's are 3.5 and 4, and one hot stream, the Cp is 3. Same is repeated here, 4, 3.5 and 3. Now, let us take the first rule which says NH should be less than or equal to NC. Here there are 2 cold streams and 1 hot stream. So, this condition NH should be less than or equal to Ct is satisfied for this hot end. So, I do not have to bother for this now. Now, the second rule which is Cph is less than or equal to Cpc has to be followed whenever we put a match. Now, I can put a match from 3.5 to 3 or 4.0 to 3, that means these 2 matches are permissible. So, in the design one, let us take this match 3 and 3.5, because 3.5 is Cpc and this is more than Cph, which is 3. So, this is permissible. Similarly, this match and this match is permissible. So, let us put a match here from 3 to 3.5. Now, question is what should be the size of the match. Now, here we see that this stream number 1, which starts from 200 degree centigrade and comes to the pinch, and at the pinch it has 90 degree centigrade, this is the pinch line. Similarly, hot stream 3 at 140 degree centigrade, when comes to the pinch this cold stream, it starts from the pinch at 80 degree centigrade and reaches to 142 degree centigrade. This is a cold stream, and the difference here, the temperature difference is 90, 80, meaning 10 degree centigrade. There is another cold stream which starts at 80 degree centigrade from the pinch, goes up to 130 degree centigrade. Now, if you see the delta H of these streams, this is 330, this hot stream, this is 217, this cold stream, and 200, this cold stream. Now, this is in a position to give heat to both of these two. Now, as we are matching 3 and 3.5 for design 1, so let us put a match between the hot stream 1 and the cold stream 3. As it can give 217 kilowatt of heat directly, so I put a match between this is heat exchanger number 1, and we keep the capacity of the heat exchanger as 217 kilowatt based on the Teachoff rule. That means, maximum heat transfer at one go has to be done. So, this is possible. So, we have put a match of 217 kilowatt, because this cold stream can take 217 kilowatt. So, why not to give heat from this 330 kilowatt hot stream directly to this cold stream, having a capacity of 217 kilowatt. So, once we transfer this heat, this stream is ticked off. This stream is ticked off, and due to this match, the exit temperature of this heat exchanger 1 is 162.33 degree centigrade, and this temperature is 142 degree centigrade. This is basically inlet temperature is 162.33 degree centigrade, outlet is 90, and here the inlet is 80 and outlet is 142 degree centigrade. Similarly, in the design 2, we have gone for this matching 3 to 4 matching, which is perfectly all right based on this Cp rule. So, here we have put a match and we call this heat exchanger number 1. Now, what should be the capacity of this heat exchanger? Here it has got a capacity to give 330 kilowatt of energy, it demands 200 kilowatt of energy. So, it is within the reach of this hot stream to completely satisfy this cold stream. So, we have passed 200 kilowatt of heat through this link. This is the heat exchanger number 1 based on the Teacup criteria. So, once we pass this heat, this stream which is a cold stream is ticked off. That means, this much of heat will be capable to rise its temperature from 80 degrees centigrade to 130 degrees centigrade. This can be seen here very easily. 200 divided by 4.0, 200 divided by 4.0 comes out to be 50. That means, delta T will be 50. So, 50 plus 80, it gives 130 degrees centigrade. So, that means, this 200 kilowatt of energy is enough to rise its temperature from 80 degrees centigrade to 330 degrees centigrade. So, this is step 1. So, we are able to put one heat exchangers and we are developing 2 designs simultaneously here for the hot end. Now, let us see the second step. Now, it is step 2. Here we have already put one on heat exchangers. Now, we will put second heat exchanger. Now, second heat exchanger can be put from hot stream to the 4th number cold stream and hot stream to the 3rd number hot stream to the 3rd number cold stream. This is perfectly permissible because Cph should be less than or equal to Cpc. So, here I use this connection, that is 3 to 4.0, this pairing, and for this I am going for this pairing in the step 2. Now, once this step is put, this is 113 kilowatt. This is 113 kilowatt. Now, from where this 113 kilowatt comes? Here it has given 217 kilowatt to this stream. So, remaining is 330 minus 217 comes out to be 113. That means, this stream number 1, which is a hot stream, has 113 kilowatt of energy with it. So, it can only transfer 113 kilowatt energy to any cold stream, and once it transfers this amount of energy, it is ticked off. That means, its all energy has been consumed. This 217 plus 113 kilowatt is 330 kilowatt. So, it is transferred from here to here 113 kilowatt, and this stream is now ticked off. Now, once it transfers this energy to here, obviously, we reach to this 200 degree centigrade. That means, if input is 200 degree centigrade, from here the output is 162.33 degree centigrade and this is 90 degree centigrade. So, it is 10 degree centigrade here, it is around 20 degree centigrade here, and this difference is also more than 10 degree centigrade. So, for the design 1, we have successfully put the second heat exchanger for the hot end design. Now, let us see for the design 2, we are matching 3 and 3.5. This is perfectly all right, because the Cph is 3 and Cpc is 3.5. So, this is satisfied. So, this is matched between this and this, we call it number 2 heat exchanger. Now, this has 130 kilowatt, this 130 kilowatt comes because this is 330 kilowatts. We have already put a match of 200. So, 130 kilowatts is left with. So, we have transferred the 130 kilowatt from the stream number 1 to stream number 3 using a heat exchanger 2. Once this much amount of heat is transferred, then this stream is ticked off. This stream is ticked off. So, here in this design 2, this stream is ticked up and this stream is ticked off, and here this stream is ticked off and this stream is ticked off. Now, this stream for the design 1, this stream is 200 kilowatt. So, 113 kilowatt I have passed. So, it needs 87 kilowatt for the design 1. Similarly, in the design 2 for this stream, it is 217 kilowatt. I have passed 130 kilowatt. So, it is 270 minus 130 is 87. Now, we will remember that for the hot end, the heating requirement is 87. So, in the third step, we will put heaters. Here I put the heater in the design 1 having a capacity of 87 kilowatt. Once I put this 87 kilowatt, this is able to heat it from 108.25 degree centigrade to 130 degree centigrade. How do I check it? 87 divided by 4 plus this. So, 87 kilowatt divided by 4 is 21.75 plus 108.25 comes out to be 130. So, the heat balance is okay and this is ticked off. So, now all the 3 streams are ticked off for the design 1. Once the streams are ticked up, it means that the hot end design using the pinch rule for the heat exchanger network is complete. So, hot end is complete for design 1. Now, for design 2, we have seen that this was the stream which was not ticked up. So, you put a heater of 87 kilowatt here, it raises the temperature from 117.14 to 142. This can be calculated and checked. So, this stream is ticked off because 87 plus 130 is 217. 87 plus 130, 87 plus 130 is 217. So, the heat balance is over here. Now, here we see the number 1 stream is ticked up, number 3 stream is ticked up and number 4 stream is ticked off. So, the hot end design, that is design 2, is also over. So, we have successfully designed the hot end and we have developed 2 designs, design 1 and design 2. In this last part of the design, we also see that the for hot end we will also develop a design which is we will call it design 1 dash and design 2 dash. Sorry, for cold end we will develop these designs. Now, after finishing the hot end design, which is separately thermally balanced, we will develop the cold end design. It should be noted that during the hot end design, we are able to meet the energy target, that means hot utility requirement, and during the targeting procedure we have seen that the hot utility requirement was 87 kilowatt and through this design we have achieved 87 kilowatts. So, we have made the target in hot end design. Here also we will see that the U minimum here is 3, because we have 3 streams and 1 hot utility. So, that makes 3 plus 1, this is n minus 1. So, 3. So, here we have, based on the units target, we have calculated U minimum equal to 3 here, and we have 3 heat exchangers here, 2 heat exchangers and 1 heater. So, as far as the units target is considered, also we have met the units target. Here in this design also we have 3 heat exchangers, out of which 1 is a heater. So, it has also met the units target. So, we have met units target as well as the hot utility target, both for this hot end design. Now, we will go for the cold end design. Now, in the cold end design, if we see, the rules have been reversed. Here the number of hot streams should be more or equal to number of cold streams, and Cph should be greater than or equal to Cpc. These are the 2 rules which has to be obeyed for the cold end design, and if one rule is violated, then we have to split the stream to remove the violation, or we can restore to cyclic matching. So, we will see that what is the problem which is arising for the cold end design. So, here also we have developed 2 designs, design 1 and design 2 for the cold end design. Now, first we see what is the number of streams rule. Ns should be greater or equal to Nc. Here there is 2 hot streams and 2 cold stream. So, this rule is perfectly valid. Now, Cps should be greater than Cpc. Now, due to this rule, this stream can be matched with this and this stream can be matched with this, but this stream cannot be matched with this and this. So, this rule prohibits me to match this stream with this and this stream with this. So, there is some sort of problem here. Now, that problem can be eliminated by splitting the streams. We also see in the last, in the design 1 dash and design 2 dash, that without splitting, if I move, then what can be done. So, here let us, to solve this, let us split this 3.5 stream into 2 parts, 1.5 and 2.0. So, here this 3.5 stream has been splitted into 2 parts, this is 2.0 and this is 1.0. Now, why we have done so? With a little bit aim, because this stream has got 75 kilowatt of heat which has to be transferred to the cold stream. Now, this 75 kilowatt of heat, if I calculate, if the Cp is 1.5, then and the stream which goes from 80 degree to 30 degree to 80 degree. So, 80 minus 30 equal to 50 into 1.5 gives me 75. So, if I split it in such a way that delta H of this stream is 75, then I can directly match this stream with this stream at once and I can tick off this. Now, if this is 1.5, then the other part has to be 2.0, other part has to be 2.0. So, I have splitted this stream and then we have matched this 3.0 and 1.5. Now, this is the match 3.0 and 1.5. So, it is satisfies this CP criteria, that is CPH should be greater or equal to CPC. Here CPH is 3 and CPC is 1.5. So, it is greater, this is greater than this. So, this match is perfectly all right and according to the rules. Similarly, in this CP table, I can break this 4 into two parts 1.5 and 2.5. So, this is 2.5 CP and this has got 1.5 CP in this. Here the CP becomes obviously 4. From this part to this part CP is 4, but for this part this is 1.5 and for this part this is 2.5. Now, this 1.5 has come with the same argument, that because I have to tick off this stream which has got a delta H of 75. If I break it at 1.5, then this is from 30 degree to 80 degree centigrade. So, it will take 75 kilowatt of it, and once I take 75 kilowatt of this, from 30 degree centigrade it will rise up to 80 degree centigrade. Okay. So, here something has to be done, so that this temperature 25 degree centigrade temperature rises up to 30 degree centigrade, and we have not put anything here. Let us see. So, by doing so, if I put this temperature becomes 65, because this has got a 75 watt, delta H is 75. So, if I put a 75 load here, so immediately it will reach to the target temperature. So, the outlet of this heat exchanger 1 is 65 degree centigrade, because it has reached to the target temperature. Okay. Now, so this is 3 to 1.5, this is step 1. Now, let us see the step 2. Now, one thing I would like to tell, that when I split a cold stream here, the value of NC becomes 3. So, this rule is violated, this rule is violated, because now NC is greater than NH. So, to satisfy this rule, I have to split a hot stream also. So, if I split a hot stream, then again the NH becomes 3. So, NH is equal to NC. So, if I split one cold stream, then one hot stream has to be splitted to satisfy this equation, and that is why this hot stream has been split. Similarly, when I am splitting this, I have to split a hot stream also. Now, we go to step 2. Now, in the step 2, this is satisfied, this part is satisfied, this part is not satisfied, this is not satisfied. So, one complete hot stream has been satisfied. So, there is another hot stream here. Now, it is obvious from this design that a cooler has to be put into this, because there is no position left to put a cooler, and at the cold end of the design the cooler has to be put on a hot stream. So, we have put a cooler here of 40 unit, because from the PTA we have seen that the cold utility requirement is 40. Similar arguments are valid here, because this is ticked off, only this is the hot stream. So, I have to put a cooler of 40 units heat capacity here. Now, coolers are always put at the end. So, we have put it at the end. So, when the temperature is 36.6 is the entry temperature to this cooler, and if the cooler takes 40 kilowatt of heat, this stream comes to 30 degrees centigrade, which is the target temperature of this stream number 2. Here also the same thing, I have put a cooler of 40 kilowatt, the entry temperature is 36.66 degrees centigrade and it moves to 30 degrees centigrade. That means, it attains the target temperature of the stream number 2. So, from 90 degree to 36.66 degree, I have to cool this by exchanging this heat with these 2 cold streams. Similarly, here 90 to 36.66 has to be cooled down by exchanging it between this and this. So, we go to the step number 3 and try to finish up the design. We have already put one heat exchanger here and this cooler. So, this part has been put into step number 2 and this part has been put and this has been put in design 2 in step number 2. Now, let us do the design. Now, if it moves from 33.66 degree centigrade to 90 degree centigrade, this or I say that I have already put a match of 75 kilowatt, the remaining is 100 kilowatt here, the remaining is 100 kilowatt here, and if I split this stream in such a way that this 100 kilowatt can be directly transferred to here, then I will tick off the stream completely. So, this part will be ticked off. So, if I take here 100, then 100 divided by, and this is the temperature difference. So, if I do it 90 to 40 degree centigrade and if the value is 2, if I calculate it 90 minus 40, 90 minus 40 into 2, it becomes 100. So, if I split this stream into 2 parts 4 and 2, this is the stream which has been splitted 4 and 2, then this part will have a 100 kilowatt energy, and when I transfer to this, this stream is ticked off, that is stream number 3 is ticked up, and this temperature has been brought down to 40 degree centigrade. Temperature is brought down to 40 degree centigrade. So, now this is transferring 100 kilowatt of heat, this is cooling 40 kilowatt. So, this is 140. So, this is 140. So, 360 minus 140, 360 minus 140 comes out to be 220. That means that this part has got 220 kilowatt of heat with it. So, if I pass the heat from this part through this heat exchanger, it will completely satisfy this stream, and this is ticked off. Now, when I pass the heat 220 to this, the temperature of this stream becomes 35 here, because this we can calculate 90 minus 35 into 4 is 220. So, this stream will be cooled down to 35 degree centigrade and this stream will be cooled down to 40 degree centigrade, and when they mix here they create 36.66 degree centigrade. So, they start with 90 degree centigrade, a part goes here cool down to 40 degree centigrade, another part starts with 90 degree centigrade, goes through this heat exchanger, cool down to 35 degree centigrade. When these two streams meet here, they make 36.66 degree centigrade, and then they pass 40 kilowatt heat to the cooler and reach the target temperature of 30 degree centigrade. So, the work of the second stream is over, that means the whole of the second stream has been ticked off and the fourth stream is also ticked off. So, in this way all of my streams are ticked off here. So, the cold end design as far as design 1 is concerned has been finished. So, here we see we first put a match between 3 and 1.5, then we split the 3.5 into 1.5 and 2, we put a match between 3 and 1.5 and then we split 6 to 2 and 4, then we put 2 to 2 match and then 4 to 4 match here. So, 3 heat exchangers are put here and 1 cooler is put here. Now, if I apply my U minimum criteria here, there are 4 streams and 1 cold utility. So, this is 4 plus 1 minus 1, this is 4. So, I am able to reach my units target as well as I am able to reach my energy target also, because through PTA I have calculated that my cold utility requirement will be 40 kilowatts. So, here I am consuming 40 kilowatt. I am consuming 40 kilowatt and my units target is also met. So, at the cold end design, as far as design 1 is concerned, I have met my energy target as well as units target. Now, if I see the design 2, so we have passed here 75 kilowatt and we have ticked up this. So, if I pass 75 kilowatt here, the remaining energy is 125 kilowatt plus 20 kilowatt, because this is 75. So, 220 minus 75, 220 minus 75 is equal to 145. So, this is 125 plus 20. So, if I see here, this stream is splitted into 2 parts, 2.5 and 3.5. This is 2.5 and this is 3.5. Now, if I see this stream has a delta H of 175 kilowatt. So, here if I see this 3.5, so 90 minus 40 is 50 degree, 50 into 3.5 comes out to be 175. So, if I break it by 3.5 and 2.5 and then transfer this heat from here to here, I will be able to tick off this completely. So, this has been broken in two parts 3.5 and 2.5. So, when I fix up 3.5, obviously the other part will be 2.5. So, I have split it like that and then this transfer heat to this 175 here. Okay. So, the outlet temperature here will be 40 degree centigrade. So, 40 minus 30 is 10 degree centigrade. Now, the outlet from this is 33.6 degree centigrade. So, 36.66 degree centigrade to 40 degree centigrade I have to put a heat exchanger. So, this exchanger is 4 and this passes 20 kilowatt of heat. Now, this part now contains 90 minus 40 into 2.5, 90 minus 40 into 2.5 comes out to 125 kilowatt. Now, this stream has now 125 kilowatt. So, using heat exchanger 2 I am transferring the total heat to this as 125 heat. So, this is ticked off and these two are also ticked off and this is also ticked off and this is also ticked off. That means, my design is complete. So, what I have made? I have made the energy target which is 40, but I am not able to meet the U minimum target which is 4. Now, here I have 1, 2, 3, 4, 5 heat exchangers I am putting. I am putting 5 heat exchangers and I am not able to meet the U minimum target. So, we have completed 2 sets of design for the cold end. The first set will be called design 1 and the second set will be called design 2. Let us check another alternative for the cold end design and let us check whether this alternative is feasible or not. The design 1 dash shows another alternative for the design of the cold end. Now, if we see this table which is CP table, we can match 6 with 4.0, we can match 6 with 3.5 and both this matches are valid, as in this case CPH is greater than CPC. Now, if we see here, then this is the hot stream which is stream number 2 which has got a Cp of 6 and this is the cold stream which is stream number 3 which has a Cp of 3.5. Let us put a match between these two streams, that is 2 and 3. So, when we put a match between these two which is termed as heat exchanger number 1, then the hot has a capacity to transfer 360 kilowatt, that is number 2 stream can pass 360 kilowatt and number 3 stream can take 175 kilowatt. So, we can directly pass 175 kilowatt through this heat exchanger which is exchanger number 1 and take off this stream. If we do so, then the temperature here becomes 60.8, whereas this temperature, the exit temperature of the stream number 4 becomes 80. Now, if you try to put another match between this and this, that is stream number 2 and stream number 4, which is valid as far as Cp rules is concerned, we see here there is a delta T minimum violation, because the hot stream has acquired a temperature of 60.8 and the cold stream 80 degree centigrade. That means, cold stream has got a higher temperature than the hot streams, and hence there is a violation. So, we cannot put a match between these two, because one end will have a temperature delta T violation. Now, let us see the other alternative available, which is 3 can be matched with 4. We can see here this violates this rule. Here the CPH is not greater than CPC. In fact, if I do this match 3 to 4, CPC is greater than CPH. But let us see that what happens if I put this match. So, I put this match 2, that is heat exchanger number 2 for this match. When I put this match, which will the capacity of the match will be 75, because the hot stream has got 75 kilowatt to give and the cold stream can take 220 kilowatt. So, I can directly put a match of 75 kilowatt. If I do so, the temperature here becomes 65 degree centigrade and the temperature here becomes 61.25 degree centigrade, and hence there is a delta T minimum violation. We should remember that this is a pinch match and I am violating this rule, and hence I can expect a delta T minimum violation, which I see here. So, 3 to 4 this match is not feasible, and 2 to 4 also match is not feasible, and hence I cannot create a heat exchanger network of the cold end by matching this way. Another alternative can be checked for the cold end design, and that alternative is called design 2 dash. Let us see whether this is feasible or not. Here we can put a match between 6 and 4, and this is completely valid because CPH is greater than CPC. So, we put a match between the stream number 2, which has got a CP of 6.0, and stream number 4, which has got a CP of 4. So, this match is called match 1. Now, as stream number 2, which is a hot stream, can give 360 kilowatts of energy, and stream number 4 can take 220 kilowatt of energy, I can put this match to be equal to 220 kilowatt. So, when I put this match, the outlet temperature of this heat exchangers is 53.33 degree centigrade here, and this stream, that is stream number 4, is ticked off. Now, another match can be put between 6 and 3.5. 6 is number 2 stream because its CP is 6, and number 3 stream CP is 3.5. So, I can put a heat exchanger, which is heat exchanger number 2 here between these two streams. Now, if I deduct 220 kilowatt from 360 kilowatt, that becomes 140 kilowatt. So, I can put a match of 140 kilowatt here, and I can tick up the stream number 2. Now, once I put this match, the exit temperature here becomes 70 degree centigrade. Now, here we will see that this is ticked off, and if I deduct 140 from 175, so I get 35. So, the stream here 75 stream, that is stream number 1, which is a capacity of 75 kilowatt, can give 35 kilowatt to this stream number 3. But when I go for matching between 1 and 3, that means 3 and 3.5, this is 3 and 3.5, this rule is violated, that is CPH is greater than or equal to CPC. So, I can expect something to happen, that is in terms of delta T minimum violation. So, if I put this heat exchanger here, stream, that is heat exchanger number 3 between 1 and 3. So, this temperature becomes 78.33, and this is 70. So, there is a delta t violation here. So, obviously, this design 2 dash is rejected because during this design there is a delta t minimum violation. So, we saw that both of these designs, design 1 dash and design 2 dash is not feasible designs. Now, the final design, we have seen that there are 2 designs for the hot end and there are also 2 feasible designs for the cold end. So, if I go for permutation and combinations, there will be 4 designs, and these designs are design 1 of the hot end, design 1 of the cold end, design 2 of the hot end, design 1 of the cold end, design 1 of the hot end, design 2 of the cold end, and design 2 of the hot end, and design 2 of the cold end. Because if I take this, then I find that the number of units when I am taking hot end design 1 and cold end design 1 is 7. Similarly, when I take hot end design 2 and cold end design 1, it is also 7. When I take hot end design 1 and cold end design 2, the number of units is 8, and when I take design 2 of the hot end and design 2 of the cold end, the number of units is 8. So, as far as number of units are concerned, these 2 designs, the feasible configuration 1 and 2, which gives 7 number of units, are better. So, this is my complete design. When I am mixing design 1, hot end design and cold end design. So, please note that hot end design 1 and hot end design 2 are not very different as far as complexity is concerned. One can take either of the 2 for the final design. Now, there is something needs discussion. Now, if I apply my U minimum criteria to this table, considering that there is no division at pinch, which is a requirement for MER design, then my U minimum comes out to be 5. This is for all the streams, that is 4 streams and 2 utilities. So, it is 4 plus 2 6 minus 1 is equal to 5. So, it tells that if you ignore pinch division, then the whole heat exchanger network should be designed with 5 number of heat exchangers or units. But whereas, when I apply my units target separately to the hot end and separately to the cold end, then I find that the minimum heat exchangers requirement is 7. So, when I am going for a MER design, so U minimum MER is 7. When I am applying my units target for hot end and cold end separately and then joining them. So, it tells something that if I am not going for MER design, then I can have a scope to decrease the number of units by 2. That means, there is a possibility that the heat exchanger network's cost will be less if I am going for a non-MER design, but a non-MER design will always consume more utilities than a MER design. Now, how to reach from a MER design to a non-MER design? So, the units target tells something about this, that why this 2 heat exchangers more are required for a MER design. Now, when we go for a MER design, we create some loops in the Hen, and in this case we will detect that there are 2 loops, 7 minus 5 is equal to 2 loops. So, there will be 2 loops for MER design, and these loops have been created because the hot end and cold end designs are separately designed without consulting each other. So, loops have been created. So, once we remove these loops, we can decrease the number of units. So, if both the loops which are present in this MER design will be broken, then the number of units will drop down to 5, but at the cost of higher utility. That means, the utility will increase when I am decreasing the number of units. So, there is a trade off between now the utility and number of units, and this trade off has to be checked. But when I break the loops, it is no more a MER design now, it is a non-MER design. Thank you.